Let's welcome Neil deGrasse Tyson. All right. You don't want to inflate him. So everything we see in the universe, the stars, the planets, the galaxies, the plants, the rocks, the clouds, us, everything you say, it's, to me, at the front of this book, is what you call the product of a remarkable asymmetry of matter over antimatter. What did you mean by that?
Can I just say something about your introduction?
Yeah.
If I may.
You may.
So I'm impressed by your persistent skepticism of all things I say.
Reporters have to, you can never really believe. You have to check and verify. Like,
Okay, I had to.
You just get, you're right every time, though, so far.
I mean, how could I possibly just come up with that unless it was correct?
What, that a building ticks off by the second? You know how ridiculous that sounds? But when they built the building, did you think, well, I have a wonderful idea. Let's move it up a half a foot, Charles, and maybe we'll get the second on the celestial clock. Okay. I don't think so.
Yeah, no, I'm sure it was not on purpose. It just is, as so much of the universe is. So, profound asymmetry. So, you just went right into the stuff there.
Yeah, well.
Okay. Just a quick note.
Yeah.
That this title, Astrophysics for People in a Hurry, I've had people joke with me about it, say, oh, was Astrophysics for Dummies already taken, you know? And I just wanted to make it clear that first, yes, it was taken, but that's, but there's nothing, I don't think there's anything, quote, dumbed down about the astrophysics in this book. It's all sort of curated, legitimate, full-up astrophysics in an attempt to sort of grant the reader a degree of fluency in modern astrophysics, so like the next morning at the water cooler, you could just be talking about.
Yeah, and like there are things in here that I had never heard of.
Really? And you get around.
I get around.
Yeah, you get around.
So I'm going to be checking. But.
So in the early universe, the temperature was very hot, and above certain thresholds of temperature, what happens is matter no longer stays as matter. It can freely move back and forth between itself and energy. And we have the recipe for this. It comes from E equals mc squared. We all know that equation. It's the formal conversion recipe for matter and energy. And the c squared is the speed of light squared. It's a huge number. A little bit of mass times that huge number gives you a lot of energy. We don't experience in our lives E equals mc squared because the energy in which we're immersed is not high enough to enable matter to go back and forth between energy and itself. That's why it took so long to discover E equals mc squared and to come to terms and to come to understand it. But it is a profound equation that manifests from the beginning of time all the way to the future of the universe, but not in our life experience. All right, so, and also let me preface it by saying, in one of the opening pages of the book, is, what do you call it, the rubric? No, what's the first
The beginning, I call it.
No.
No, I know what you mean.
No, the publishers have a word for the page that has a thing on it.
Yeah. Well, it says
that's
here,
the dedication.
For all those who...
That's the dedication. Oh, you want to read it? Okay.
I mean, for all those who are too busy to read fat books, yet nonetheless seek a conduit to the cosmos. Yeah.
But that's not what I was looking for, though. No, no, 2 pages beyond.
2 pages beyond.
Yeah.
Contents.
Yeah.
Preface. Preface?
Okay.
Oh. Yes. The universe is under no obligation to make sense to you.
Yeah, that's it.
Signed by you.
That's what to make that clear. So the universe is under no obligation to make sense to any of us. So I will be saying things and you'll say, that doesn't make sense. Just remember what I just said, okay? Okay. What we've learned is that the universe is what we measure it to be, not what we want it to be, not what feels good, not what only has to make sense to our five senses. Our five biological senses forged in the plains of Africa, you know, 1 million years ago, 500,000 years ago, whatever, what's the latest the biologists tell us, is those senses, to prevent us from getting eaten by a lion, are very different from what you need to grasp the universe. And so this is why mathematics is so potent, because it takes us out of our senses and enables us to still probe the reality of what the universe is. So here's what goes on. If matter and energy can go back and forth, this is how that works. I have a blob of energy and it decides that it wants to become matter, and it does. So all this energy becomes matter.
What do you mean it decides? It goes, and then it thinks, what should I like to be today? Or?
It happens spontaneously, and it depends on what the temperature is.
Okay? Cool.
What's that?
It's hot and then it gets cold.
Yeah, so if the temperature drops too low,
Yeah.
then it's not going to happen. The energy will stay energy, and whatever matter was around at that time will stay matter. So watch what happens. We now have high enough energy that if you converted this pocket of energy into mass, E equals mc squared, you get enough mass to create particles out of it. Okay? So get a very low, take an electron, for example. That's very low mass among subatomic particles. So you can ask, how much energy does it take to make an electron? Write that number down. If you don't have that much energy around you, your energy will never become a particle. Ever. Okay? So, in the early universe, there was so much energy, every particle could be made. So watch what happens. You have a pocket of energy, it becomes mass. And the only way we know that can happen is if it becomes a particle and an antiparticle pair. Matter and antimatter.
Antimatter is the opposite of the first thing?
Yes.
Oh.
In every measurable way. Okay, so the opposite of an electron is a positron. It looks just like an electron, but among other things, it has the opposite charge of an electron, positron. Okay? Every particle has an antiparticle.
Does a neutron have an anti-neutron?
Yes.
Does a proton have an anti-proton?
Yes. And so you might say, well, what's the opposite charge of a neutron? Because the neutron has no charge.
Yeah, I know.
But you look at what the neutron is made of. It's made of quarks that have fractional charges that cancel each other to get zero net charge on the neutron. So an anti-neutron has all those same quarks, but the antimatter version of those quarks on the inside.
What will happen if these two kiss?
If you take matter and antimatter and put them together, they annihilate and become pure energy, and the matter disappears entirely.
What do you mean disappear? Does it leave something over?
No.
Not even like a little boing? Not a light, a photon, something?
Yes. So you take the particles, matter, antimatter, identical particles, except that they're matter, antimatter, bring them together, they disappear, and that matter becomes energy, and all that's left is energy, right in that pocket, right there. That happens all the time in the center of the sun. It happened everywhere in the early universe. Now here's the rub. You have all these photons of light. Oh, by the way, I have a photon joke. Can I tell it?
Tell the photon.
Okay. A photon checks into a hotel.
Not a bar. A hotel.
Not a bar. No, this has to be a hotel.
It can't be racy because this is a family.
I got this.
Okay.
I got this. Photon checks into a hotel. The bellhop comes up and says, do you have any luggage? And the photon says, no, I'm traveling light.
And if the bellhop were here tonight, he'd laugh a big fat laugh.
Yes,
Does he get it?
indeed.
Okay.
So when I say pocket of energy, let's just simply refer to photons because they carry energy. All right, so a photon turns into matter. It's a matter-antimatter pair. Matter-antimatter come together, they make a photon. It's symmetric, okay?
Okay.
So,
Wait a second, does that mean that if every matter part met every antimatter part, they all would go and you'd be left with just light?
yes, there would be no matter in the universe, only light.
Oh.
Okay, so now,
As in, let there be light.
yes.
Except there's nothing else after that. So sort of a very short story.
Let there be light and we're done.
Yeah.
Yes. Yeah.
Yeah, I
So,
would take that right out of Genesis and start over.
yeah. That would be a very short Genesis
Yes,
right
yeah.
there. So you have all this energy in the form of photons becoming matter and back and forth, and there it goes. As the temperature of the universe dropped, you reach a point where you can no longer make particles with the energy you have. But you have all these matter and antimatter particle pairs that eventually find one another and annihilate and make a photon. But we're still cooling the universe. So according to our known laws of physics, in the cooling universe, every matter and antimatter particle pair would have annihilated, made a photon. The photon would have cooled, and no more matter would have been made, and we would have had an entire universe of just light. But that is not the universe we occupy. We can start like a band here.
No,
you know?
I'm saying we apparently are the exception.
Yes.
Yes.
So, mysteriously, we call it symmetry breaking, just because that's what happened. We're just describing what happened, not that we fully understand why it happened. One out of basically 1 million of these reactions, 1 out of 1 million, the photon did not make a matter-antimatter pair. It just made a matter particle.
It was very...
You're trying to find out why.
Yeah.
And I'm just saying, it is that, okay? So, 1 out of about 1 million makes a matter particle without the antimatter counterpart. So now the dance card, the dance hall, has 999,000 partners that can pair up.
999, 9,000, yes. Well,
1,999,
Yeah.
and there's 1 left over. So everybody else becomes light, and that 1 has no antimatter particle to mate with. And it is frozen out of the universe and has become all the matter that we know and see today.
So everything that we are...
It is a profound asymmetry
Wow.
in the early universe.
We're the stuff that didn't get a date.
Correct.
Doesn't that strike you as an extremely fragile interpretation of all that there is? I mean, it's like being around by the skinny skin of your chinny, whatever that thing is.
Except in the concept of multiverse, we would have many, many universes. All the laws of physics don't have to be the same in each universe. So there could be plenty of universes where the dance card was full and they just have light in them. And you are not in that universe saying that it was just a chance occurrence.
Oh, well.
You are in the universe where
I don't care
it
about
happened.
the other ones. I'm just interested that our universe, the one that we know and live in, is such a fragile arrangement
No,
originally.
it's not. Well, it doesn't have to be. It may be, but it doesn't have to be,
Yeah.
and it is unlikely to be. And can I give an obscure example that will settle this?
Yeah.
Okay. Line up 1,000 people and give them a coin, and everybody said, flip the coin. And about half will get tails, half will get heads. If you got tails, sit down. That's 500 left, approximately. Mm-hmm. Have them flip. Half get heads, 250 of you sit down. Now we're left with 250. Do it again. Go from 250 to 125 to 60 to 30 to 15 to 8 to 4 to 2 to 1. Okay? In this experiment. It's not an unthinkable experiment.
Mm-hmm.
This person who survived this exercise flipped heads 10 consecutive times. Now here's what journalists do. They go up to that person and they say, how do you feel? Well, I knew I had felt that heads energy halfway through, and I was feeling it, and did they ask anyone else if they felt that heads energy? No, they only interviewed that guy. Okay?
You come
Wait,
on
I'm not done.
All right.
Wait, so that person says, boy, I was lucky to flip heads 10 consecutive times. Well, essentially every time you do this experiment, somebody's going to flip heads 10 consecutive times. So you want to say, oh, this is a special universe in which that happened? No, because of the nature of the fact that you have 1,000 experiments happening all the time, there's going to be one where somebody flips heads 10 consecutive times. Every time you do this experiment. That does not make it special. Just because somebody flips heads 10 consecutive times every time you do the experiment. So you're in a universe where this weird thing happens at the beginning and you want to feel all heads energy about it. And I'm saying, in a multiverse, there could be 999 universes where that did not happen. And you're in the one that did, and you want special credit for it. I'm not giving it to you.
All right. Let me move on to another thought. In the second sort of section of this book, this is something that hasn't really occurred to me. I mean, once upon
Wait, the book doesn't have sections.
I know it doesn't. I just meant the next thing I noticed.
Okay.
That once...
Can we stand the book up? Like this?
Yeah.
Can we do that?
Stand up.
Can I do that? Is that allowed?
Yes.
By the way, if you didn't know it, you all get like a free book tonight. Did you know this? Okay, everybody. Excuse me, just to be clear. I signed every one of your books, okay? And those are the books that are part of that series. If you look on that page that are signed, there are 6 or 7 cities there. I'm going to be in each one of those cities giving one talk. And all those books are signed, and I'm not signing any other books but those.
So it's a limited edition.
Yeah, basically, that's right.
And if you open your book and your signature, his signature is not in there, and you're the lonely one, you can go off and start another universe. Speaking of universes, there was a time when people believed that the heavens up there were the province of God, and whatever was going on in there was unknowable, and it would be basically sinful to find out. You point out that with gravity, well, why don't you just briefly, Newton comes along and then everything changes.
Yeah. So you look up and the planets are going forward against the background stars and then backwards, and we call that, there's a word for that, retrograde, and they do a loop-de-loop, and nobody understands it. And the fact that no one understands it is presented as evidence in some bits of scholarship, as evidence for the divinity of the heavens, because that is the handiwork of God, and we are mortal, and God is immortal and omniscient, and so we can't possibly know the mind of God. Mm-hmm. So you're just content just in your ignorance watching planets. There was some attempts at this with the geocentric epicycles and all of this, but it was well accepted that you'll never understand. Newton comes along, writes down equations of motion, equations of gravity, and kind of on a dare, he invents integral and differential calculus. Then he turned 26. This is why Isaac Newton is my man, okay? Just to make that clear.
Okay.
Among many reasons. But so he writes down these equations, and he can now demonstrate full knowledge of how, why, and where, and what the planets are doing. And so potent was his new theory of gravity that it worked for moons of Jupiter orbiting Jupiter, not just planets orbiting the sun. And this was the first indication, maybe this is not just a local truth, that maybe it applies across the universe. And this was a little bit of heresy, thought by some, that, in fact, Newton was accused by some say, Isaac, you've left nothing for God to do. And that's simultaneously a dig at him, but also quite a compliment, that he can actually understand the mind of God.
Well, this is where it got interesting. Then you went off. I mean, everybody knows that gravity is ubiquitous and universal. But then you went and asked about chemistry and physics, constants, and I hadn't really thought about that before. Is the chemistry of the sun and the chemistry of the earth and the chemistry of the furthest thing you can think of, are the laws about bonds and pairings and so, are they the same everywhere without exception?
It was not obvious. There's no tablet in the sky that required that the laws of physics we discover on Earth's surface would apply elsewhere. If they were different on Earth than on the moon and on the sun, I suppose we could deal with that. But what a remarkable fact that it is the same.
Well, wait a second. Like, you've seen that thing on Jupiter, that storm that never quits? The big red thing, the big...
Yeah, we call it the red spot on Jupiter. We call it Jupiter's red spot.
Okay.
Because that's how we roll.
That thing is...
Spots on the sun, sunspots. See? See how... Any geologists or chemists in the audience? Biologists?
But
you should be jealous of this fact. Because you guys name stuff that nobody knows what the hell you're talking about. Okay, and you know what I'm talking about.
Isn't it suspicious to you that a storm there could go on for 350 years without a break, and we never have storms that go on for 350 years without a break? We don't even have storms that go on for like 6 weeks without a break.
So, first of all, these storms are, when we have storms, it's in our atmosphere, so that's gas.
Yeah.
We rotate once a day, and so that rotation creates what we call a Coriolis force, which moving air that moves from one latitude to another actually has its direction deflected because of this Coriolis force, and this is why storms rotate in one direction counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Just a quick aside, I was channel surfing one day waiting for a movie to come on at the top of the hour. I had 15 minutes. I hit a football game, and they just ended the game at a tie, and they just started overtime. I said, that's about right. Let me just watch this. How bad could it be? After the necessary exchange of possession, it became sudden death overtime. And then one of the teams, Cincinnati Bengals, got within 50 yards, and they kicked a field goal. And the ball rotated up. It hit the left upright of the goalpost and went in. And I said, ooh, wait a minute. And I said, which stadium is this? What's the latitude? And I looked at the orientation of the stadium. I did a calculation, and then I tweeted. And I said, the overtime winning field goal by the Cincinnati Bengals was likely aided by a 1/3 of an inch deflection to the right imparted by Earth's rotation.
Which
people lost their minds. People, the local sports channels, and so the point is, if you were going north-south at all in the northern hemisphere, you will deflect to the right, no matter what you're doing. Okay, that's why you have a low pressure system, and I'm a ball of gas below it. If it's low pressure there and I'm air, I'm going to head for the low pressure. That's how this works. It's low pressure. That means it's higher pressure out here. So all the pressure is going to send me in that direction. But I'm crossing lines of latitude. And so Earth's rotation will deflect me to the right. How about air that's above it? It says, I see a low pressure system. Let me go to it. So it goes to it and it deflects to the right. So all this air deflects to the right, but it's still trying to get to the center of the low pressure system, but it can't because it keeps getting deflected. And all this deflection becomes this cyclonic energy that turns into a storm. And that is how you get hurricanes, tornadoes, what do you call it? Cyclones.
Cyclone.
Okay?
So we're back at Jupiter finally.
Yes, we are.
Yes.
So now watch.
Oh, good.
So this happens in the gas.
Yeah.
All right. The Coriolis force is heightened if you spin faster. Okay? And so what is Jupiter? It's 100 times bigger than Earth. More than that, 1,000 times bigger than Earth. It's like, it's 10 times across, cubed. So it's 1,000 times bigger than Earth. It's mostly gas. And it rotates once in about 10 hours. You want to talk about ferocious Coriolis forces? We have storms that last weeks here. Hurricanes that pick up and they get weeks on this little speck we call Earth that has this much atmosphere on it. Go to a planet that rotates twice as fast, is 10 times as wide, 1,000 times the volume, and is mostly gas, and you're complaining that it lasted 300 years?
You are really good. All right, let me I'll grant you that the speed of light is universal, obviously. Angular momentum, conservation of energy, sure. What about...
well, this chapter, just to be clear, he's coming from a chapter called On Earth, as it is in the heavens.
Why? You said... Can you spontaneously levitate and hover above the ground in a lotus position like Michael Keaton in Birdman? In the, the beginning of Birdman when he's with his underpants. Forget the underpants, just the levitation. This for some
reason... Is that your first thought when you think of someone in a lotus position? Is Michael Keaton in that movie?
Yes.
Okay.
Yeah.
It's just, there's certain things you just can't do because they're prevented by all known laws of physics. You cannot spontaneously set yourself into motion unless you push off of something else or you lose some kind of mass that was within you. So rockets, when they take off, they're ejecting mass out the other side, okay?
Wow, so do you saw Birdman? Did you just leap up from your seat and say, can't do that, can't do that?
No, there are movies where I'm prepared to suspend my disbelief, yes. Like, just as an example, I was asked about the movie Guardians of the Galaxy. And they asked me, well, the ships that are going through space, they make noise, and clearly, does that upset you? Because in space, where there is no air, no one can hear you scream. But no one can hear you explode either, nor will you hear engines or anything. And so they said, does that upset you? And I said, I bought into the idea that this movie has a talking raccoon that shoots artillery from heavy weaponry off its shoulder. If I can accept that, I'm good with whatever else they deliver in the film. So I have the capacity to accept movie magic. Yes.
What would happen if someone served you a hot cocoa with whipped cream and you see no whipped cream in evidence?
Oh, don't get me started.
Okay.
Oh, wait. Let me finish about levitating.
Please.
Right. So all the people that are levitating, it's some kind of an illusion that they're not telling you about. Okay. Period. Okay. Now, but if you really want to levitate, if this is really important to you, I tried to calculate how many cans of beans this would require. Then you got to kind of hold it in.
Yeah. Right.
Then let loose.
Suddenly.
Yes. And in principle, for the duration of the thrust, you can levitate briefly.
But this would argue against the lotus position because there would be an opening so suddenly that there'd be too much, too soon, too fast, and therefore no rise.
Oh yeah, you wouldn't, well, you could stay there if it just kept coming in, right. So it's not impossible to hold a lotus position. It's just unlikely you're doing it for these other ways that are described.
I see.
Yes.
The cocoa?
Cocoa. Oh, yeah. So there was an incident in Pasadena, California. I was there. I don't drink much coffee. I don't have a relationship with caffeine. But every now and then I'll be delighted to have a nice cup of hot cocoa. And I went to one of these coffee houses, with the chalkboard out front. And so I had, the kind I'm talking about. They're all over Brooklyn. You trip on the chalkboards in Brooklyn. So I'm in there, I order hot chocolate. And I ordered it with whipped cream, of course, right? And it comes to the table, and there's no whipped cream. And I said, I ordered this with whipped cream. And they said, oh, we put it on. And I said, well, where is it? Oh, he said, it's sunk to the bottom. I then said, either the laws of physics that apply everywhere in the universe are suspended in your coffee shop, or you didn't put whipped cream on my hot cocoa. And he looked indignant.
Really?
Now, to his credit, rather than continue to argue with me, he intended to prove me wrong. Whoa. So he went into the kitchen, brought out the whipped cream, scooped it up, popped it in my hot cocoa, and it bobbed once and floated atop. And there it was.
Did you invite him?
Of course, whipped cream has to float. Because, first of all, before it was whipped cream, it was cream, okay? And old-timers remember, what does cream do in unhomogenized milk? It floats to the top, and you skim off the cream, leaving behind skim milk, okay? This is how that works. Now, you take the heavy cream and then whip it, putting air into it. It is not going to sink on any known liquid devised by man, okay? So,
all right.
So here's my point. The lesson there is,
Yes.
I'm a fan of the edict, if an argument lasts more than 5 minutes, then both sides are wrong. I think that applies maybe 85% of the time, but it's a good rule. It's a good tenet to carry with you. Now watch. This is how science works. One researcher comes up with a result, and that is not the truth. No. A scientific emergent truth is not the result of any one experiment. What has to happen is somebody else has to verify it, preferably a competitor, preferably someone who doesn't want you to be correct, such as my waiter. He went out to prove me wrong and got the same result that I had declared. We can call that the beginnings of an emergent truth about whipped cream. Now we need someone to do it in Asia and in Europe, and then you get a trend, and you can then declare that a consensus of observation and experiments has emerged in the scientific community. Whipped cream floats on hot chocolate.
And that waiter today is getting a PhD in buoyancy. Let me go on to a question that came up later in the book. Just how voidy is the void of space? So it looks pretty empty out there between galaxies, just a lot of black, it seems anyway. If you stepped into intergalactic space, by the way, what might happen to you?
You would die.
Yep. But you might see stuff, and this is the list. Well, I had never heard of any of these things. Dwarf galaxies, runaway stars, faint blue galaxies, hot clouds that emit X-rays. Let me just ask you about some of them. What is a dwarf galaxy?
It's a little galaxy.
Well, that I figured.
Didn't we go through this already? Our words mean what they say?
But
we're past that already.
There are galaxies that you see, the ones the Magellan saw, smudges in the sky. Those are huge things.
No, well, they're dwarf galaxies.
Those are dwarf galaxies?
Oh, yeah.
Oh.
Oh, yeah, they're like 100th the size of our galaxy.
So how many dwarf...
They far outnumber big galaxies.
They do.
Yeah, so maybe we shouldn't be calling them dwarfs because they're the common size galaxy. We should just be called giants, perhaps.
Giants galaxy.
And they call them regular.
Right?
That's how that works, right?
What is the difference?
Right?
How
Like
many
this?
stars are in a galaxy?
Our galaxy has several 100 billion stars.
And in a dwarf galaxy?
At most, a billion, but more typically hundreds of millions. These are small numbers compared to full-up red-blooded galaxies. So tiny are dwarf galaxies, and we tend to find them in the vicinity of big galaxies, but you know what happens? You know, they orbit the big galaxy, but their orbits are not stable, and they do a death spiral in, and they get eaten by the larger galaxy. And we have a term for that. It's called galactic cannibalism. In fact, there are streams of stars that we see in our own galaxy that have the same trajectory as one another through the stellar system that is the Milky Way. So and you follow it and it comes back out and back in again. And so this is evidence that this was once a fleshy but dwarfy galaxy that we ate, ripped apart. And now the stars are just trying to have the last bastions of a memory of what they once were, because they're getting stretched apart by what we call the tidal forces of our galaxy.
Does the Milky Way have dwarfs?
Yeah, the first science essay I ever wrote was called "The Galaxy and the Seven Dwarfs," because at the time the Milky Way had 7 dwarf galaxies in orbit around it. And then, but dwarf galaxies are very small; they're hard to detect. And since then, we've discovered, a couple dozen more. So we might be up above 2 dozen dwarf galaxies in our vicinity, basically nearby. So the point, getting back to the void, is you look out in the void and say there's nothing there. Well, what are you invoking to declare that it's a void? Is it your eyes? Well, let's bring in a telescope. Are you using visible light? Is that a visible light telescope? Bring in an X-ray telescope, an infrared telescope. Bring in the spate of senses that science has developed that transcend the 5 native senses we have through our human physiology. And that power enables us to decode the universe not as our senses receive them, but as our detectors.
There is an amazing chapter, or coda, somewhere in the back, where you find out how human beings finally sensed what they couldn't see. That there is a rainbow of color that we all can see, which are waves of different lengths. They take you from whatever it's, Git B, Vibbo, Roy B, Viv. So Roy B, Viv.
Roy.
Red to...
Repeat after me, Roy.
Red,
Roy,
orange.
G, Biv.
Red, orange, yellow, green, Biv. Blue, indigo, violet.
Violet, you got it.
But it's weird.
Just a quick thing. Roses are red, violets are violet. Right? Is it? I mean, who came up with violets are blue? Where's that? We have a name for that color.
That was a desperate poet looking for a rhyme, I think.
Don't be violating laws of physics just to make the rhyme, okay?
I was going to say...
You know Mark Twain's edict that I love?
What is it?
First get your facts straight, then distort them at your leisure.
Well, let me just finish this thought, and then I've been commanded to ask questions.
I'm sorry.
At the end, there's this moment where somebody has to figure out that there might be something redder than red or somehow more than violet. Now, we only have eyes, but this particular person used a thermometer.
It was brilliant.
It was brilliant.
Brilliant.
Yeah.
Okay, so Isaac Newton is the first to understand that white light is composed of colors. So he takes white light, puts it through a prism, and he gets Roy G. Biv. Actually, the indigo he had a mystical fascination with the number 7, so he wanted to lay down 7 colors.
Oh.
But indigo is just really blue-violet, all right?
Okay.
But anyhow, we'll give him his indigo because he did all that stuff before he turned 26. So if you invent calculus just on a dare, we give it to you, all right? We'll give you indigo if you need to have indigo. So he's got the colors, and then he took those colors, merged them back together, and he got white light out the other side. That's some freaky stuff. That's just freaky.
Yeah.
That red, orange, yellow, green, blue, violet equals white, okay? So we're good there. William Herschel comes around later and says, I wonder, just to even ask this question, I wonder if the different colors of light have different temperatures. So he laid down the spectrum with sunlight prism, and he put a thermometer in each color. And then he had an 8th thermometer. I don't know if he used one and did the experiment 7 times, but he had another thermometer that he used as the control thermometer. You put that over to the side where there are no colors. And that would presumably just measure the room temperature. So he knows enough to even think that this is an interesting exercise, and he's got a control thermometer. And he just puts it over to the side of the red, out of sight. And then he watches the thermometers. And the control thermometer goes through the roof.
Yes, it does.
And he's looking at it. And he says, something must be coming through the prism that I cannot see. And he describes this as light unfit for vision.
Yeah. Yes, he does.
He discovers infrared light with that experiment,
And then another guy
which the human eye cannot see.
It's
And
amazing.
if you go to the hardware store and get an infrared bulb, and you turn it on and it looks red, you're seeing the red light that is also emitted from this infrared bulb, and the heat that you feel, your eye cannot see, that's all the infrared that you're buying when you pay money for that bulb. Yeah.
And then some other guy put a piece of paper on the other side of violet, and it turned dark, and he pretty much
photographic paper.
Photographic paper.
And he found that it responded in the way you would normally respond by putting photographic paper in front of visible light. So he concludes, that was somebody else later.
Somebody else, yeah.
Right, and says, there's something beyond the light. There's something less than the red, infrared, something beyond the violet. And thus was discovered ultraviolet light. And so to pose the question in the first place was a stroke of brilliance. To then trust your measurements on a level where you then declare you have made that discovery is a whole other thing.
Yeah. Here's the thing about this book.
Well, that story is told in the book, just so people get a sense of the history of the history of puzzlement and the history of discovery rolled up into one.
I'm not going to ask you about anything else because it's time for questions and answers, but I would have, so just so you know what else is in here, there's dark matter, which is this mysterious thing that's out there, which we...
Dark matter is everywhere. Yeah, okay.
Dark energy. One of the questions he asks is, why are so many heavenly bodies round? Is there anything in the universe that's perfectly round? What's going on between planets? Why is there still debris coming in when the Earth seemed to have scooped up everything after 4.6 billion rotations? Something at the end called the Copernican principle. All of it is really, but never mind. The question is, the universe is 14-something billion years old. We've now seen galaxies that are 13 billion years old, and somehow that might suggest that the universe is expanding and that there is more and more universe all the time.
Well, first of all, the universe is expanding, and there is more and more observable universe all the time. The universe at its edge is expanding at 1 light year per year. That's how that works. And so in a billion years, the edge is not going to be 14 billion light years away. It'll be 15 billion light years away. So we got that. Okay. So now, galaxies 13 billion light years away, we are seeing light emitted by that galaxy, and that light has been traveling for 13 billion years. Okay. Yes, that galaxy emitted its light when the universe was 10% its current age, and in fact was much smaller than it is today. Now you said the current paradigm is 14 billion year age of the universe. You said that with a little bit of, oh, you'll come up with something different later. The proper way to say that is the current measurements of the age of the universe. That's how that works, okay? Paradigm came into our lexicon in a big way in the 1970s with a book written by the science philosopher Thomas Kuhn. What's that?
Joel Barker was the futurist who actually made that famous. Started with Kuhn's work.
There's a dangerous woman in here. Who is this Joe Barker of whom you speak so dangerously? Remember what happened to the guy who didn't put the cream in the coffee?
So this book, The Structure of Scientific Revolutions, sort of introduced paradigm as a way that scientists sort of gather around a paradigm and they all sort of accept it. Although then something different happens and better data comes along, that we all gather around a different paradigm. That happened basically until the dawn of the age of modern science, which I date from Galileo and Bacon, Francis Bacon, where when you experimentally measure something to be true and it's verified, that is a truth that does not later turn out to be false. Period. It's not how science works. It's not like, oh, that's going to be false, now let's all crowd around this. You would be left with that impression having read that book. But the book got that very wrong for the age of modern science. Before then, sure, because people just thought stuff up and called themselves scientists, and that was with philosophers. And you turn out to be profoundly wrong when somebody else thought up something better, and then everybody's wrong when we finally started taking data. It's all about the data. Okay, so everything you described is just perfectly fine. Yes, it finds galaxies. The next telescope, the James Webb Space Telescope, is tuned to live in that regime, to find galaxies being born in the early universe. So there'll be a whole lot more data coming back from the early universe when that telescope gets launched, lands at its observing point, and gets turned on. So there's nothing you said that's odd or weird. That is the universe we live in.
Okay, question
Sure.
is, he heard something you talked about God on CBS television, and he's thinking about near-death experiences, and he wonders whether these deep mysteries are interesting to you.
Okay, so one of the things we know from research in psychology, as well as just practical matters in the conducting of scientific experiments, is that one of the lowest forms of evidence you could possibly invoke is eyewitness testimony, which is odd because it's one of the highest forms of evidence in the court of law, which disturbs me greatly. Mm-hmm. So if you come from a lab to a science conference and say, this is true, we say, how do you know this? Because I saw it. Well, that's really the end of your talk, and you just leave. And then we say, come back when you have a chart recorder, or you have to just give me something that does not have to flow through your senses, because your senses is some of the worst data-taking devices that exist. And science did not achieve maturity, modern science did not achieve maturity until we had instruments that either extended our senses or replaced them. And Galileo, it's not an accident that we have modern science as I've described it, experiment, verification, these tactics, these methods and tools, began with Galileo and Francis Bacon, and Galileo was around 1600. That was the invention in that period of the microscope and the telescope. So it's not an accident that all this sort of came together at that time. So now we have people who are in the act of dying, and they come back from life, and they report on mental experiences. And that's intriguing. It's intriguing. But because it is in the realm of eyewitness testimony, you can establish it perhaps as a personal truth, but it will take more than that to establish it as an objective truth. And an objective truth is the kind of truths that science discovers. And it's the kind of truth that is true whether or not you believe in it, okay? It exists outside of your culture, your religion, your political affiliation. Personal truths, if I may consider that, would be, okay, Jesus is your Savior. That's your personal truth. You cannot convince someone else that Jesus is their Savior in an objective way. You have to persuade them. You have to persuade them in some cases by war, right? Look at the wars that have been fought between religions that did not agree about who was their respective saviors. Sure.
Although if I walked on water, made you unblind, created loaves and fishes out of nothing,
that would be amazing.
I think.
And we would investigate that, and we would say, "Whoa!" Yes, we would. So it would be an amazing thing. And then if we cannot account for that by any other known laws of physics, and it's only happening with you, we'd wonder if you were like alien or something first, right? But no, it would be so easy to demonstrate divinity if in fact you had the power you wanted to display. But getting back to the gentleman's point, so part of this issue is, what does it mean to be dead? Okay, it used to be, did you fog a mirror that was held up in front of you while you were laying there on your bed, all right? And if you didn't fog the mirror, you were judged to be dead. They would put you in a coffin, and in some parts, it is told, there's a string that they put into the coffin as they buried you, and they put it over a tree branch and connected to a bell. If you woke up, you would pull the string, and that's where you get the term dead ringer, okay? You would pull the string, and you come rescue me because you buried a living person, okay? So, then it was you're dead because your heart stopped. Well, we know why a heart beats. It's electrochemical. So you do pa-chunk, the heart beats again. We got that one. Okay? Well, is it when you're brain dead? Well, you can be brain dead, but your heart is still beating. And we can keep you alive. Are you dead yet? Well, no, because your heart's still beating. Is your brain functioning? No. Okay, I can tell you this, that if you're dead long enough so that your brain is deprived oxygen, and then we bring you back, you're not talking about seeing any lights because you're brain dead, okay? So, plus, this often happens to someone who is deathly ill to begin with, and where are they? They're in a hospital. And if they go into cardiac arrest or something critical, they take you from your hospital bed to an operating table. And what is sitting above an operating table? Lights! Bright lights, okay? And so, if you say, oh, I was dead and I came back and I saw lights, maybe it's not all the cases, but it's many of the cases, okay? Now, there were skeptics who tried to do an experiment. There are people who say they left their body, and they saw, we got some of those?
Montesquieu.
So here's what when was Montesquieu?
He got rear-ended by some guy in a horse, fell off, flew up into the air, looked down at himself in agony, watched his wife come over.
Wait, they had rear-end collisions in the era of horses?
Montaigne, not
Still,
Montaigne.
they had rear-end collisions in the era of
Well,
horses?
you ride a horse with a guy behind you who's riding too fast. It's like a cab situation.
Okay, I didn't know that. Okay. Okay. So, I didn't know that.
Well, I love stopping you mid-sentence.
Rear-end collision with the horses. Where was I? So there was an experiment. So there's some descriptions that are part of this near-death experience literature where they come above and they see themselves down there on the bed, okay? So what they decided to do is for people who are about to die, they would write a message facing upwards to the ceiling above the bed and suspend it there. So if a person goes above their bed and looks down, they'd be able to read the message. So when they rejoin their body, they should then tell us what message they saw. That's never happened. It's just, no. That's a no. Now, I have a cousin who when her father died, was alone with him in the room, and he's in an open casket. And she's otherwise completely rational, okay? I'm not saying this is a crazy person. Completely, she's a real estate agent, okay?
Speaks for itself.
Okay. Among other okay. So she's in there. She tells me of a conversation she had with her dead father. And I said, was it in your mind? No, he sat up and spoke to her. I said, what was the conversation? And she said, well, he said, don't worry about him. He's in a better place, this sort of thing. So this is her eyewitness testimony. I'm not going to say it's wrong. I'm just saying it's not scientifically useful. That's all I'm really saying here, okay? I told her, next time this happens, ask these questions and not those questions, okay? Don't say, are you happy? No, saying, are you wearing clothes? Where are you? Where did you get your clothes? What temperature is it? Just ask questions. Like, this is an amazing scientific experiment you could be performing. So that's my lesson to all of you, that if you find yourself in that situation, okay? Because if a dead person sits up and starts talking to me, oh my God, my iPhone is coming out. I'm getting chart recorders. I'm gonna be all up in that as an experimenter, okay?
All right, up in the balcony, whoever that was, yes. Question is, can you help us understand a multi-dimensional universe? What would be the dimensions we are unaware of?
Any dimension higher than the 3 that we're familiar with, or the actual 4 that we're embedded in. We live in a 4-dimensional world. And that might sound a little flaky or freaky, but consider the following fact. You have never met someone at a place unless it was also at a time. And you have never met someone at a time unless it was also at a place. That requires 4 dimensions of coordinates.
Wait. What about in a dream?
Is the dream happening inside your head?
Yes. I don't know when.
So the only point is, we know intuitively that we need 4 dimensions to localize someone to meet up with them. Especially when, well, only 2 dimensions if you don't have tall buildings. You have tall buildings, you need the 3rd dimension. So you don't say, I'll meet you at the 20th floor of, on 721 Park Avenue. What time? Okay? There's a full 4 dimensions going on there. So just I want to convince you we live in a 4-dimensional world for that reason. Okay. It may be that these 4 dimensions are manifest to us, but that in fact we are embedded in a higher dimensional space. And string theorists on the frontier of this exercise are hypothesizing at least 10 dimensions to account for everything we see in the universe, even if we do not directly measure those dimensions themselves. Now, with your permission, may I go on a dimensional journey with you? May I? Might take you on a journey?
A dimensional odyssey.
Odyssey. Are you ready?
Yes.
Okay. Are we ready? Just get ready for this. Okay. So, I'm at my desk, and the desk is a surface, okay? And I start putting pages down on the desk. I'm tiling them on the desk. And then I run out of room. I have exhausted the 2 dimensions of the surface of my desk. We have ways of accommodating this problem. And so we have page organizers that go upwards. So now when I don't have any more surface area of the desk, I can enter a 3rd dimension and put pages there. If you are an ant embedded in this 2-dimensional world of the surface of my desk, and you fill up the desk with these sheets of paper, the ant will say, there is no more room. And I say, yes, there is. Watch me. And I take a piece of paper off the desk, put it in the page organizer, and according to the ant that's embedded in the 2 dimensions, that page disappeared. It disappeared into a dimension that ant does not have access to. What a brilliant invention this is. You can put practically an unlimited number of pages, far more pages above the desk than on the desk. So access to a 3rd dimension is an extraordinarily useful storage device for a 2-dimensional creature.
Does the ant trust you that what it cannot see is nevertheless there?
You have to then talk to it about this extra dimension. And then it will have to just trust you.
Yes.
Because watch what happens next. I now have my 3-dimensional room, and I'm filling it with boxes. Now I've run out of space to put the boxes. But now a 4-dimensional alien looks at us and says, I got this. Just move it into the 4th dimension. What are you talking about? And the alien comes in, reaches in, takes one of the boxes, and then the box disappears. Disappears. It went into a 4th dimension. And this was captured in the film Monsters, Inc. Did you guys see this film? These are monsters that work in a door factory, and they make these doors, and they open the door, and it is the door of a kid's bedroom or their closet. And they step through, and they're in the kid's closet. And then they scare the kid, because that's their job. They're monsters, okay? This doorway is a portal through the 4th dimension and then back to the 3rd. So imagine a new storage system where you just go to Home Depot and buy a door. And that door is your portal to a 4th dimension. You open the door, put your boxes, close the door, you look on the other side of the door, there's nothing there. So this is what's going on when you have access to higher dimensions.
Wait, don't you have to then talk to somebody? Because as far as you know, if you're a scientist and you need data, what you have is something that you had, it's gone, and now a voice says, I've got this.
Yeah, if
that data?
If it's a voice from the 4th dimension, I'm going to listen to it.
So does every dimension
I'm not going to say, no, you're
narrator?
lying. If there's a voice coming out of the 4th dimension and makes one of my boxes disappear, I'm thinking it's got more power than I do and more knowledge of the space-time continuum. So I'm going with it.
Does that mean that in order for a scientist to credit another dimension with real existence, it will need a testifier from beyond? So you need a dimension plus a dimension voice?
Yeah, a dimensionless voice. Yeah, that comes from another place. Mm-hmm. Now, there are things that happen in quantum physics that kind of defy our sensibilities. Like particles pop in and out of existence. They defy any rational attempt to understand it. Particles can be entangled with one another. A particle can be here, and there's a barrier, and it can spontaneously show up on the other side of the barrier at faster than the speed of light. All of this is just mysterious. Let me ask you, suppose you have a sphere, and I live in a 2-dimensional world, and you take this hollow sphere, so it's a shell, and you pass that sphere through my 2-dimensional universe. How will I describe that? I will say, this point just appeared out of nowhere. Oops, now it's a circle, a small circle. And that circle's getting bigger by the moment. Oh my gosh, it reached a maximum size. Now that circle is just shrinking. It's shrinking. Now it's a point. Now the whole thing disappeared. This would be completely freaky to a 2-dimensional being. But it makes complete sense if you live in 3 dimensions and you pass a sphere through my universe. So who is to say that some of the mysterious things we are describing accurately, but don't otherwise make sense in a higher dimension. And these are just the manifestations of higher dimensional phenomena in our world. And that's an aspect of what these higher dimensional physicists are trying to establish.
At this point,
Now I want to totally blow their minds, if I can,
Oh, sure.
if I may. But you got to stay with me on this, okay? A point has no dimensions. There's no height, width, depth, so it has 0 dimensions. A line has 1 dimension, length, okay? A square has 2 dimensions, sort of height and width. A cube has 3 dimensions, height, width, depth. We got this. Now follow me. A line is 1-dimensional, but it's bounded by 2 0-dimensional things. Those are the points. 1 dimension bounded by 2 0-dimensional points. A square is 2 dimensions bounded by 4 1-dimensional sides. A cube is 3 dimensions bounded by 6 2-dimensional sides. So in other words, the dimensions of your sides are going up. Your line is bound by 0-dimensional points. Your square is bound by 2-dimensional lines. I mean, by 1-dimensional sides. The cube is bound by 2-dimensional squares. Okay? So we're going up 2, 4, 6. 2 points, 4 sides of a square, 6 sides of a cube. And each side is 1 dimension less. They're squares on the sides of a cube. They're lines on the side of a square. They're dots on the sides of a line. Let's go up to a 4-dimensional cube. A 4-dimensional cube has 8 sides. A regular cube had 6 sides. We're going up by 2. A 4-dimensional cube has 8 sides. And each of those sides is a 3-dimensional cube. 1 dimension down from itself. In the same way, each side of a 3-dimensional cube is a 2-dimensional square. So when you get to 4 dimensions, the sides are 3-dimensional surfaces. And you can take this all the way up. And our brains can't picture what we call a hypercube, in some circles a tesseract. We can't picture a volume bounded by 3-dimensional cubes. What does it even mean? This is because we evolved in the plains of Africa, just not wanting to get eaten by a lion. Our neurosynapses are ill-equipped to do the distance on this. And this is why we invent mathematics that can take us there.
well, the mathematics can help us imagine it, but if we want to credit it with reality, then you have to design an experiment that somehow touches your own world.
Yes. So you can invent something that you can't see if it has testable consequences in ways that you can see. That's perfectly allowed. Not a problem. Mm-hmm. Oh, and by the way, there's some people that say you cannot prove a negative. Some people like coming after. Generally, you won't hear a scientist say that. Mm-hmm. It's others, like philosophers and people who like criticizing scientists, but who are not scientists. They'll say you can't prove a negative. We kind of do that all the time, okay? But we don't use the word proof. We demonstrate without any further discussion that the negative is true, okay? So here's an example. There's a cave there. Is there a bear in the cave? I don't know. I'm not going in to find out, okay? I'm going to set up cameras and see if a bear comes out, okay? So I set up the cameras all throughout summer. No bear goes in and out. But then I take down the camera. Maybe a bear went in there to hibernate. So here's what you do. You set up powder outside of the cave, something that will record a footprint. And you just monitor this month after month after month after month. Do it for 12 months. Look up in the charts how often a bear has to eat and how long it would take a bear to die for not eating. If the period of time you waited is long enough so that there are no footprints, you conclude that there is no bear in that cave. I just demonstrated a negative sufficient enough for me to no longer pose that question and go on to another problem. But if you are so distracted that it's not a formal proof of a negative, then you could just keep sitting there wondering while the rest of us decode the nature of the universe.
We have, for the last bear in the cave, I guess, let's see.
Oh, by the way, maybe the cave is not a closed cave.
It might have a rear door.
It may have a back door.
Yeah.
Okay, that's possible. I suppose that's possible. So then the assumption that there's no bear in the cave would be wrong. But
Or the cave could have a cave, and that cave could have another cave. You see, there's just so much to worry about.
Right, and so you will sit there, arrested by your own capacity to doubt an experimental reality.
Yes.
While, like I said, the rest of us go and keep making discoveries.
Well,
Yes.
we have time for one more question, and that person at the very end, underneath the exit sign, hand prominently raised, not the one waving it, but the woman in the yellow shirt, still with her hand up and wondering if I'm looking at her.
Yellow?
She's looking back and forth.
Well, it's not a yellow shirt.
It's not a
That's
yellow
the problem.
shirt. That's
Yeah.
it.
It's a horizontal striped shirt.
Oh, okay.
Yeah.
Really? Oh. Oh!
But repeat it.
That, this was an art major or something. I'm right, I guess. Yay. If you had one last question to answer this evening, what would that question be?
So you misunderstand me. Oh, that wasn't your question. But can I at least answer that? No. Okay, go.
In your career, if you had one last question to get answered, what would you
Oh. If you're in your career as a scientist, if there is one question that you wish to address before you go to the great cave with the bear, or wait forever for the bear to come out and stay there, what would that science question be? Or did you like your previous question better?
Yeah, okay, so I'm going to give an answer, but then I want your permission to give you a kind of a cop-out answer. So I'll give both, a full answer and then a cop-out answer. My full answer is, I wonder if, in fact, the human intellect is sufficient to actually decode the full operations of this universe in which we live. And it's not specifically an astrophysical question, it's just more, we are an intelligent species because we defined ourselves that way. We don't have the benefit of another species to compare ourselves with, against whom we might fail miserably. And so when we compare ourselves to chimps, we sit up righteously and say, we have poetry and the Hubble telescope and philosophy, and the chimp just stacks boxes to reach a banana. Yet there's only 1% difference in our DNA. But then you'll say, what a difference that 1% makes. And I would say maybe that 1% DNA difference corresponds with an equally small difference in the intelligence between a chimp and humans. And you say, I can't believe that. No. Well, imagine some other species that visits us that's 1% along on that same scale, smarter than us. Consider, the smartest chimp does what our toddlers can do. And there's no way you will explain to a chimp, I'll have dinner ready at 6:30, can you pick up some juice on the way home? The simplest human thoughts are inconceivable to a chimp. And their talents are about what our toddlers can do. So let's get back to this 1% smarter alien that we've discovered. Corresponding this analogy, we now say, what would we look like to them? Well, they would roll Stephen Hawking forward after combing the human species, and they'd say, this one is slightly smarter than the rest because he can do astrophysics calculations in his head like little Timmy over here, who just came home from preschool. Oh, Timmy, you just composed 3 sonnets. Isn't that cute? Let's put it up on the refrigerator door. Oh, you just derived the fundamental law of calculus. Isn't that cute? Put it up on the refrigerator. Their simplest thoughts would transcend our deepest thoughts. And maybe to them, it is obvious what dark matter is and dark energy. Maybe to them, particles popping in and out of existence is a trivial exercise in their understanding of the multidimensional space-time continuum. And we are here groping at the sides of a wall, not knowing how tall, wide, or deep it is, because we have the limits of the human physiology evolved off the plains of Africa just to try to understand the entire universe. So I lose sleep on that question each night. So that's my...
Wait, did you almost say at the beginning of that answer that you are wondering, maybe something of a Mysterian, that you're not sure?
I'm not sure.
The universe is so complicated that it may be more complicated than we can ever fathom.
No, that's the hubristic way to say it.
Oh.
That's not how I said it, okay?
How did you say it again?
We might not be smart enough, okay?
Not
If you're hubristic, you would say, we are smart, but the universe is just really complicated. That's not what I said.
Right.
I said we might not be smart enough to figure out a universe that could be trivial to the brain of a more intelligent species.
Okay.
So check your hubris at the door. Otherwise, you will not bask in the cosmic perspective that so much of this discussion brings upon us. So, may I now give you my cop-out answer? My cop-out answer is, I think often about the questions we do not yet know to ask because discoveries yet to come, but when they arrive, will put us in a new vista, a new place to stand, enabling us to see questions undreamt of and unimagined before we got there. So when I, again, lay awake at night, I ponder what kinds of questions lay beyond our reach. Because the questions that we even know how to pose, they're there. Those are not even interesting to me anymore because we knew how to ask the question. I want to know the question that is beyond everyone's reach. And by definition, I can't because we haven't gotten there yet. But that doesn't mean I shouldn't dream of that frontier. And
That sounded like a coda to me, I gotta say. Like I could hear the orchestra playing through.
May I offer a better coda?
Yes. And then we'll let you go. But I
Yeah, we went here long.
this.
Sorry, we went long. Try not to ever forget that the history of this exercise, this beautiful exercise where we find out where we fit in this great unfolding of cosmic events and phenomena, that the larger grows the area of knowledge. Okay? The bigger that area grows, just remember, so too grows our perimeter of ignorance. It may be that as much as we think we know, as much as we know, as much as the more things that we ultimately learn, for all we know, we could be steeped in the center of infinite ignorance, which then provides job security forever for scientists, right? Robert Krulwich.
Neil Tyson.